We're now recording. So this is reviewing worksheet 1, power functions. Now remember, if your n value is less than 0, so like for example, n could be like -1, generally the graph's going to look like this in the first quadrant. If your n is between 0 and 1, say n is 1/2, like a square root function, it's going to start at the origin and rise, but rise kind of slowly. And if n is greater than 1, like say n equals 2, it's going to start at the origin again, but it's going to increase more quickly. So what you're going to notice, being a little bit more detailed, is that if you drew a tangent line, that's not a tangent line. A tangent line, right? A tangent line touches the curve at one point. The tangent lines get less steep as x gets bigger for the second scenario. For the third scenario, if you draw a tangent line, as x gets bigger, your tangent line gets more steep. That will always be true for the third scenario. And then for this one, your tangent lines are always negative, not positive slopes, so you're decreasing. But they actually get larger, the values, and they get closer and closer to 0. They tend to get more flat. So those are some phenomena that you really want to be aware of. When you try to graph x value is less than 0, you're going to have to be very mindful. Can it fit in the domain of the function? So if you're even rooting, forget about it, because you can't even root negative numbers, otherwise it'd be imaginary. Also, you want to consider symmetry. So if a domain does exist for x less than 0, that's great. But you also have to understand, like, hey, is it going to be a mirror image? So is it going to be reflected about the y-axis? Is it going to be reflected about the origin? Is it going to have origin symmetry? So there's some things we have to kind of work through. So let's actually go through these right now to make sure you got these. And then if you have questions, please stop and ask, or you put in the chat as well if you're more comfortable with that. So for 1, 2, and 3, here n is between 0 and 1. Here n is between 0 and 1. Here n is greater than 1. So because we're between 0 and 1 for 1 and 2, we expect this to happen. And to really understand that, just think about the y equals root x, right? Y equals root x is the same as y equals x to the half power. Well, yeah, if you have x to the half power, if you were to plug in numbers for x, like say plug in 1, you get 1, plug in 4, you get 2, plug in 9, you get 3. Yeah, y is increasing, but not as quickly as it would for something like 3. 3 is kind of more like y equals x squared. Even if x to the 4/3, they behave in a similar fashion. So we expect that to happen. So 3 was like the third scenario, n's bigger than 1. 1 and 2 are like the second scenario, n's between 0 and 1. Now, what's going on the left side? I'll do this in red for a bit of contrast. On the left side, you're cube rooting, remember, for number 1. Can you cube root negative numbers? Absolutely. You can odd root negative numbers, so it is defined. Now, is it odd or even? What if I take the cube root of negative x? Or just take the cube root of negative 1, or cube root of negative 8. Is the output positive or negative? The output's going to be negative. You're going to pull out a negative from this cube root. So cube root of negative numbers are negative. So we expect our curve to look like that on the left side. So it's going to be rotation about the origin. Here we're fifth rooting x to the 4 power. Now, notice that you're raising x to an even exponent. That always makes the output positive, or 0 if you plug in 0. You're never going to get a negative output when you're even exponent. When you're doing even exponent, like 4 here, even power, that's what I meant to say, I guess, you're not going to get a negative output. So you're always going to be fifth rooting a positive number. So that's an even function. Plus, if you're plugging negative x, replace x with negative x and try to do in the 4th power and then fifth root it, you get the same thing. Remember, even functions, we had this on the summer assignment, f of negative x equals f of x. So by switching the sign of the input, the output stays the same, you're going to get that y-axis symmetry. For odd functions, remember, f negative x, if you switch the sign of the input, if the output changes sign, you're getting that origin symmetry, which is the case for number 1. So you really have to look at this case-by-case basis. I mean, you could generalize, I suppose. You could say, hey, if I have an odd exponent, my domain's going to be defined. I'm sorry, if I have an odd denominator, my domain's going to be defined for x less than 0. Absolutely. And then once that happens, if I have an odd numerator, it's going to be odd. Or if I have an even numerator, it's going to be even. Yes, you could generalize that. But if you try to memorize that, you're going to drive yourself nuts. So you really want to understand numerically what's happening. And that's what I'm trying to do here. I'm trying to give a good sense of understanding numerically. Like here, I'm doing the cube root of x4. Yeah, I'm doing an odd root. I can put in negatives, not a problem. And it's going to stay positive because I'm raising to the 4 power. So it's going to look like this. And now, why are we spending the time understanding how these graphs look? We are going to be doing derivatives. Derivatives is a big part of this class in the first semester. Derivatives, in essence, are slopes of tangent lines. We're going to have that discussion later in this unit. In order to accurately draw a tangent line and know whether it's a positive or negative slope, and if that slope is increasing or decreasing as you go along the curve, you got to know how the curve looks. You can't always rely on the calculator. You're going to have to be able to know some stuff without the calculator too, and be able to recall this quickly. So that's why we're spending the time on this. So that's 1, 2, and 3. Any question about 1, 2, and 3? Nope. Okay. So make corrections if you had any errors, and don't worry if you made mistakes on your homework that you submitted. Don't worry about it. Maybe that's something I might, if I see it, you're having problems, I might just shoot you a quick message or put a comment in school. Hey, come by during the office hours, or just remember, you know, if I see there's a common misconception, I might make a comment about that. So I'm going to go through those by tomorrow because tomorrow I don't teach. So I'll go through you guys' work and put comments on there. For number 4, now in this case, you are even rooting. And by the way, it ends between 0 and 1. So we expect the curve to look like this. I'll do this in blue. And you're doing the 4th root of x cubed. Well, it's not defined for negatives. We're clearly not defined for x is less than 0. So forget about it. You just leave it as is. That's all you got. So don't touch it. Just draw the first quadrant and move on. For 5, you're odd rooting and raising to an odd power. So you're doing the cube root of x to the 5th. If you want to simplify and pull out like an x, I mean, if you want to do that, I guess that's fine. But just for the sake of doing the graph, I think we're okay with leaving it like this. N's bigger than 1. Looks like this. And you could plug in negatives. That's okay because you're doing an odd root, you're doing a cube root. But the output's going to be negative though, because you're raising negative x to the 5th power, which is negative x to the 5th, and then you're cube rooting, so you can pull out a negative. So the output will be negative. So your curve is going to look like this. You might remember y equals x cubed, that graph. That's an odd function. And so x to the 5, oh, yikes. X to the 5/3 follows the same curvature as x cubed. They're really not that much different. I mean, of course, the y values will be different, right? But the curvature, same thing. X to the 5/4, again, n's bigger than 1. So you're going to have this. Now you're doing the 4th root of x to the 5th power. Now we're not defined because you're going to be even rooting. We're not defined for x less than 0. So leave your answer like that. Don't touch it. That's it. It's like you know, you're square rooting. You just leave it like that. But of course we're not square rooting because we're doing x to the to the 5 force power. So it's a little bit different, but that's what we got going on there. So, and then finally 7, 8 negative exponents. Obviously n's less than 0 here, n's less than 0 here. Now that's 1 over the cube root of x squared. And of course it's 1 over x cubed. We have negative exponents, so we expect this to happen in each case. Sorry, for this case, for each of those equations. Just gotta be careful with the words I use sometimes so I don't confuse you guys. Now remember, we can square negative numbers and then it becomes positive and you can cube root it. So this is defined for x less than 0. And of course that one too. Of course neither of these are defined for x equals 0, which is why we have this curve. So we do have these vertical asymptotes here. Now on the left side, this is an even function because if you plug in negative x for x and cube root it, that still comes out as being positive. So actually it's going to look like this. So that's an even function. This is an odd function. You have x cubed. If you plug in -1, it's -1 now. So you have that. So again, very, very important that we understand the curvature of these. That's going to make a big difference when you're trying to do some of the more advanced stuff that we do in this class and a lot of the calculus principles. We have to have a clear picture of how these graphs will look and how these equations behave graphically. Very, very important. Okay, so any questions about that before we move forward? No? Okay. Now we're going to look at the textbook work. Let's do that. And I'd imagine there probably be some questions, but I'm going to anticipate what some of the questions will be. Sorry, I'm just looking at another screen. I actually have 2 screens going on here. So I look at some of the work here and I do some of the work on Zoom. It just makes this a lot easier to do the online classes when I have multiple screens. So my apologies. Just give me 1 sec here. Just let me open that up. Okay, so let me clear this. And let me pull up the homework. So going back to Schoology again, there were some book problems, 43 to 50 all. Probably close that. Let me open up the images. Any questions about that anyone just wants to ask right now that anyone's was confused about? Or if anyone's put anything in the chat.
This is more.
Go ahead, Belle.
This is more of just a general question. But I remember from the summer assignment, you said that anytime we reference a graph, we should draw it. So I drew all 8 graphs. Like, did you want us to do that, or is that not necessary for homework?
I'll tell you when I want you to, I guess. Just put it that way. If I don't tell you, then don't do it. Yeah, that's actually came from Mrs. That came from Mrs. Blanford. She is very, very strict about that stuff. It is good to do that. I don't think it is good practice. And so if you do, I do that. You know, when I started becoming older and more mature of a student, I would do that, and I'd be a little more detail oriented. But that's just my OCD kicking in. I'll tell you. If I don't tell you, then don't worry about it. I think in this case, I think it would have been fine if you didn't. But I do think there would be some scenarios where you probably want to. So I'll just we'll treat it case by case. So yeah. So default, if you don't see anything, don't do it. Well, with that said, let's actually talk about 44 H and I. So it looks like we have a question. Okay. Yes. Okay. Good. Someone read my mind. Okay. So thank you for that question who posed that. So let's do 44 H and I because those were a little weird, and we didn't quite talk about that in the notes. Before I hit up H and I, let's just talk about what's going on at x equals 1. That might be good. So let's look at DEF actually, because that might help us in understanding H and I after that. So for D, as x approaches 1 from the left, so we call this the LHL, the left-hand limit. As I'm approaching 1 from the right side, what is y getting closer and closer towards? It's definitely getting closer and closer to 2. Now remember, it doesn't mean that x equals 1. F of 1 I know is 1, because you see a dot there. I'm not asking that question, or the book's not asking that question. All I'm just curious about, what is the left-hand limit? What is y approaching as I'm getting closer to x, as x is getting closer to 1 from the left of 1? So if I were to write all this in words, all this means that, what does y approach as x gets closer to 1 for values less than 1, or the left side, the left of 1, the left of x equals 1, being a little more specific there. That's a lot of words to write. What does y approach as x gets closer to 1 for values less than 1, or left of x equals 1? That's why we have limit notation. So we don't have to write all those words. It's just too much. Because that little superscript indicates that we're plugging values of x that are a little bit less than 1, like 0.9, 0.99999, and so forth. Well, clearly we see from the graph that as x gets closer and closer to 1 from the left side of 1, from the left of x equals 1, or values of x a little bit less than 1, y is getting closer to 2. That's true. Absolutely true. And we call it the LHL for short. Now the other one is analogous to what we just did for D, but now it's from the right side of x equals 1. So values of x that are a little bit bigger than 1, like 1.1, 1.000001. So we're getting closer and closer. Well, we actually stay at 1. So that's also true. We call this the RHL, the right-hand limit. Now, F is a big one. In order for the limit to exist, and we're going to really drive this home today, for a limit to exist, the LHL must equal the RHL. You need to have that to happen. Does the LHL equal RHL for x equals 1? Absolutely not. It does not. The LHL is 2 and the RHL is 1. Those are not the same. When they're not the same, you say the limit does not exist. So F is a true statement. The limit cannot exist if they're not going to link up, right? For x approaching a certain number without the superscript. Without the superscript, we're looking at both sides and they're not linking up. So forget it. So hopefully that's okay with DEF. With that in mind, this should help for H and I now. Let's look at H and I. Oh, by the way, of course, G is true because the LHL is 0, the RHL is 0. Yeah, but that was a different x value. Let's look at H. Now, first off, these two right here, it's a little confusing. These are interval notation. They're not coordinates of points. These are both interval notation. So if you're confused about that, please, get the, think of that mindset. That's what I'm asking you to do. Yes, that is correct. Someone asked, so if the RHL and LHL exist on their own, but the combination of them, like they're not equaling the same thing, then right, it doesn't exist. That's 100% correct, yes. So whoever posed that question, you are correct. Yeah, so yeah, of course you have an LHL, you have an RHL, you have those numbers, but if they're not the same, the limit does not exist. So let's look at H now. So first of all, we're looking at interval notation, right? So this is telling me when x is between -1 and 1. It's not the point negative 1 comma 1. Don't think of that. So if you thought it was that I apologize for may not make that clear in the homework. I should probably put a little hint or a little FYI or something like that. So that's simply an interval notation. So let's look at the graph from negative 1 to 1 for x. Non-inclusive, remember if we were inclusive, you'd have brackets, right? We don't have brackets. So could I find the limit of any x value between negative 1 and 1 on the graph? Again, not including negative 1 and 1. The answer is yes, we can. Like for example, what if I want to find the limit as x approaches negative 0.5? So c is negative 0.5 because c is between negative 1 and 1. Negative 0.5 is between negative 1 and 1. Could I find the limit as x approaches negative 0.5? Sure. The left side and the right side get to the same place. Totally. Could I find the limit as x approaches 0? Sure. I have that right there as well. Could I find the limit as x approaches 0.9? Sure. Now, so the answer is going to be true for h. Now, what would have made that false? What would have made that false is if I had replaced the last number here with 1.5. Why would that have been false? If someone wants to answer that. Would the limit have existed? Well, go ahead.
I was gonna say because it's like two different segments of like the graph, I guess. Like they don't converge. So
At what x value was that happening at?
At 1.
Exactly, right. So now x equals 1 is in that interval, is included. And that's a problem because our limit did not exist as x approached 1 when we had our discussion about DEF, right? Or, let me backtrack a little bit. What if I did a bracket here? Again, the answer would have been false. Because our limit, and we use DNE for short, does not exist as x approaches 1. So that would totally would have been false. Let me pose this question to you guys. What if I had a hole here at x equals 0 and I had a point at 0, 2, so the point jumped off the graph? Would h have been true or false?
Wouldn't it still be true? It just
Good.
f of 0 wouldn't be.
Yeah, so it doesn't equal the limit, but it's still true. Yeah, the limit would exist, absolutely. H would have been true even if we alter the graph in this manner. So it's all about approach. That's the point we're trying to get at. Now, there's another thing we're going to talk about called continuity. When you see points jumping off the graph, or you see like a disconnection here, these won't be continuous. These scenarios. We're going to have that discussion later in this chapter. And that's when it really kind of reinforces a lot of the stuff we do early in the unit. So a lot of the stuff we do, just so you know, really gets reinforced. So don't feel like, okay, after 2.1, 2.1 is so separate from 2.2. Absolutely not. They're all intertwined. So even if you're feeling a little shaky, it's okay. Remember, this is calculus. It's new. Calculus is not supposed to be the easy subject to learn. I think it's a very learnable subject, but it just takes time to absorb it and start seeing connections, and of course, giving a chance to reinforce the stuff. So this stuff does get reinforced naturally. That's why I love this class. It just has a nice flow to it. So again, it's going to be true because even though you have a break at x equals 2, who cares? The limit as x approaches 2 was still 1 because the LHL equal RHL. So the bottom line is this. Does the LHL equal the RHL for all x values in the given interval? That's what this is really telling you, this mathematical stuff. That's really what the question is. Does the left-hand limit equal the right-hand limit for all x values? And the answer is yes, it does. For these intervals, because they're not inclusive and didn't include points where the limit did not exist, So the limit did exist at all those. At any x value in between -1 and 1, non-inclusive, and 1 and 3, non-inclusive. So hopefully that clears it up if you're a little stuck. And more happy to give you more practice of this too, so you guys can feel more confident with this. So trust me, that's all we're doing this month is limits. Another thing that just came to mind right now, we have a test scheduled for Thursday of next week. That's going to get moved, just so you know. I don't know, I think my initial plan was a little bit ambitious, so we're going to be flexible, obviously, because we're going to spend all of 2.1, not starting 2.2 today. We're going to spend a lot of time 2.1. I would like to knock out 2.1 if we can. So I think we do need to get to the notes because it is 9:28 now. So any other questions about homework? Okay, that took a little longer than I thought, but I think we need to have that discussion though. I thought that was important. Okay, cool. And remember the other parts of the homework were right here. And they were kind of more the same stuff like, hey, was PM -2, what's the limit? And I gave you the answers there. So hopefully having the answers kind of helped you understand what's going on too. Obviously, I mean, there's not much work. There's no work to show. You just give the answers. Ultimately, we are going to have work to show work. And it's nice when you can show the work and you get the answer, then you feel confident. Great, I've got this. Or if you don't get it, then try to reverse engineer. Like, okay, how did they get that as an answer? Look back at your work, like, oh my God, I can't believe I did that mistake, or I totally misunderstood something. You know, that's when you learn a lot, when you have that self-discovery. And of course, if you get stuck, ask me and I'll point it out to you and help you out, or to kind of lead you to the answer. Okay, let me stop sharing for a sec. Let me